So today, in this concluding lecture, we will introduce the laws of the black hole mechanics, which are also known as the three laws of black hole thermodynamics, which show that, even classically, black holes behave similar to thermodynamical systems, which allows to make deeper connections that are further developed in quantum settings. So, we'll start with the introduction of the surface gravity for a Killing horizon. So, as you can recall, a Killing horizon is a null hypersurface whose normal is a Killing vector. And as we have shown by rigidity theorem, event horizons are necessarily a Killing horizon under certain assumptions. In general, so in a stationary spacetime, we have a stationary Killing vector field, which is stationary with respect to the asymptotics. So, since we consider asymptotically flat spacetimes, that is, they behave as Minkowski, we have a stationary. So the stationary Killing vector field with respect to asymptotics will look like as d over dt and k squared at r plus infinity goes to -1. Good. So, as we have shown, and as we have discussed on the example of Kerr, the Killing vector field of the Killing horizon is not necessarily the stationary Killing field, and in fact can be different. So we write it as k plus omega h m. So k is the stationary. So Killing vector field, and this is axial Killing vector field. So, in our more or less standard charts, it is d over d phi. This proportionality constant is we identified with angular rotation. Angular rotation of the horizon. As you can remember from the discussion of the Kerr black hole. Okay, so yes, we take the proportionality coefficient as 1 here, so we take psi equals k plus something, because it's convenient for us. It's convenient because it is convenient for us to relate to asymptotically flat stationary Killing vector field. Good. Now, if you recall, psi squared on a horizon, on a null hypersurface, on a Killing horizon, is 0, because it's normal to it. And therefore, its gradient on the null hypersurface would exist only in the normal direction. Because since it is constant on the null hypersurface, if we take a directional derivative along any tangent direction to a null hypersurface, it will be 0. And the only remaining direction is the normal direction. So we have that the gradient is proportional to the normal itself. It is convenient for us to take the proportionality, to write the proportionality coefficient as follows. So, okay. So we write dxi squared on n equals minus 2k xi for some function kappa. Yeah, this is kappa. For some function kappa on the null hypersurface. We call this function kappa to be the surface gravity, and we call the surface gravity to be this coefficient kappa. So let us now discuss the interpretations of kappa. So first of all, let's start with the geometric one. Note that the gradient can in fact be rewritten by the use of the Killing vector field equation. So yes, if you put indices, we have xi nu equals 1/2 of xi nu d mu xi nu equals, sorry, 1/2 equals 2. Equals 2 equals minus 2 using the Killing field equation. The xi of xi mu. So, therefore we have that d xi of xi equals chi xi. So therefore, surface gravity kappa measures the failure of affine parameterization of xi on the null hypersurface. Of xi equals d over d lambda to be affinely parameterized. Good. Now, let us find the surface gravity. Good. Now, before going to a physical interpretation of the surface gravity, let us do a simple computation for the rest inertial black hole. Okay, so rest inertial black hole. Recall that its metric in going Eddington-Filkenstein coordinates is given by minus delta over r squared dv squared plus 2dv dr plus the sphere. So delta is given, so delta gives us the two horizons. So we can write it as r minus r plus r minus r minus, where r plus and the r minus are the exterior and the interior horizons. So let's compute the surface gravity. We know that xi is given by d over dv, and its square is nothing but the minus delta over r squared. So xi squared is minus delta over r squared, and xi squared on r plus minus, that is on each of the horizons, is 0. Let's compute its gradient. First, notice that xi with the lower, index is dr. Next, let's do the gradient of xi squared. So on R equals R plus minus. So this is the same as 2 delta R cubed minus delta prime R squared R equals R plus minus. Notice that the first term necessarily vanishes. And we have it is the same as minus delta prime and delta prime is 2R minus R plus R minus equals which equals to R plus minus minus R minus plus over 2R plus minus squared. We can see two different limits here. So first of all, we see the extremal limit. So recall that extremal case is given when the charge equals the mass. So we have Q equals to mass, and therefore the two horizons coincide. So then the surface gravity is 0 there. That's one thing. Secondly, also notice that kappa, which in general we define to be a function, is actually a constant on the horizon. We, as a next step, as a zeroth law of black hole thermodynamics, we will show that in fact it is constant on the killing horizon in general. Okay, the second limit is the limit of the Schwarzschild black hole. So we have Q equals 0, which means that R minus is 0 and R plus is 2m. Good. In this case, we have only one horizon, and we have kappa given by one over 4m. So we have related to Schwarzschild to the Schwarzschild black hole, well, in Schwarzschild chart. What happens with the general analytically extended Schwarzschild solution, that is the Kruskal black hole? So let it be the exercise. So for the Kruskal extension of the Schwarzschild, we have two horizons, the future horizon and the past horizon. So we can show that, well, the horizons indeed happen at r equals constant, at r equals 2m, but this corresponds to two different horizons. So we have h plus and h minus. So h plus is given by u equals 0. H minus is given by v equals 0. And the surface gravity on the future event horizon is kappa, because this region is also covered by the Schwarzschild black hole chart, by the Schwarzschild chart. So however, so on the past event horizon, so that is on the horizon of a white hole, we have surface gravity to be negative, -1 for m. Because remember, the white hole is the time reverse of a black hole. So since surface gravity is defined with respect to time-like Killing vector field, it's proportional to it. So it is linear with respect to rescaling of the time-like vector field. It will be of the opposite sign. So it's opposite sign, -1 over 4m. Now, recall that the future and the past event horizon have a non-trivial intersection. This non-trivial intersection is called the bifurcation surface. So, how do we reconcile it? Well, as simple as it is, on the bifurcation surface, which is a two-sphere for Kruskal, the Killing vector field vanishes. So therefore, the definition of a surface gravity on the bifurcation sphere becomes irrelevant. Okay, now let us see the physical interpretation of the surface gravity. Now we will show that, in fact, it's a force per unit mass that is to be applied at infinity to hold a test particle at the event horizon. So let us consider the trajectory of a point particle at rest at the vicinity of the event horizon. So trajectory is given by, so since our space-time is static, well, since the space-time is stationary, the trajectory of the point particle is given by the time-like Killing vector field k. So such orbits are not geodesics because the particle, in fact, has an acceleration. So the acceleration, of course, requires a force. And let us consider the trajectory of the particle in the very vicinity, that is very close to the event horizon. So let us assume that the particle is held by some inelastic string attached to infinity. Similarly to the geometric meaning of kappa, measuring the failure of xi to be finely parameterized, we can also link it to the force required to keep it there. So let F be the force of the string. The force of the string to keep the particle that is attached to the infinity, to keep the particle at the event horizon. And then we have that F tends to kappa there. So F tends to kappa as R goes to RH. This is simple to see. This is simple to see from the Schwarzschild black hole. This is simple to see from the Schwarzschild black hole, where we consider the geodesic equation in Schwarzschild coordinates. inertial coordinates, and then we will find that the acceleration with respect to infinity, with respect to the asymptotic observer, is given by f per unit mass. Now let us compare this notion to the local acceleration of the particle at the event horizon. Of course, these two things are different. In fact, on the event horizon, the particle would experience an infinite acceleration. Such picture is not very physical, because then the string attached to infinity must be able to hold the infinite tension. So let us see that. So let's calculate the local acceleration. Local acceleration. So let the forward velocity of the particle be given by u mu equals k mu over its squared, so that u mu is normalized such that u squared equals -1. The acceleration is then given by the derivative along the forward velocity. So we can define local acceleration. So we'll call it a being the derivative, that is the proper time derivative of the forward velocity, which is given by directional derivative of the forward velocity along itself. And this is then given by k times dk mu minus k squared plus k mu q minus k squared squared k mu d mu k squared. So in the first term, the Killing equation gives us that the first term we simplified by the Killing equation. We have that this equals to, we have switching the order of nu and mu. This is the same as k squared d So the second term is in fact 0, because here we have that this equals to k nu equals to 2k nu k mu of d nu k mu, where this is in fact antisymmetric. We know that by the Killing vector field equation, this is the same as minus 2k nu k mu d mu k nu, and therefore this whole thing is 0, because we are contracting the symmetric with the antisymmetric parts. So okay, well, plus 0, and therefore we have that, a mu equals the d mu of minus k squared over minus k squared equals, equals 1/2 of the logarithm equals 1/2 of the d mu of the logarithm of minus k squared. So since k squared goes to 0 on the horizon, of course this should diverge. So for the Schwarzschild black hole, k squared is given by minus k squared is given by 1 minus 2m over r. So, and therefore we have that a mu is given by dr, which diverges at 0. And yes. Through which diverges on the horizon. So to check that this is indeed a problem, let us find its norm. So the norm is therefore given by GRR, AR, and this is m squared R4 1 minus 2 m over r. And it is divergent on the horizon. So a physical string would break. So a physical string holding such a particle at rest would in fact break because it would have to experience the infinite tension. Good. Now let us move to the laws of the black hole mechanics. Okay. So let us start with the laws of the black hole mechanics, which also known as the laws of black hole thermodynamics. So if you recall from usual thermodynamics, so the zeroth law its zeroth law states that there exist stable configurations of the thermodynamical system that are characterized by the macroscopic parameters, in particular including the temperature. So here we will associate the temperature with the surface gravity. And this will be the main theorem stating its law. So before proving this theorem, we will start with a smaller proposition. So consider an algebraic congruence that contains the generators of the null hypersurface. Which is also a killing horizon. Then all the geometric characteristics of the correspondence, that is the shear, the expansion, and of course the rotation of these null congruents vanish. Then Okay, let's prove it. Okay, so first of all, since the generators are orthogonal to the null hypersurface, we have the rotation equals to 0. We have proved the statement in one of the previous lectures. So. Okay, now let us consider the killing field, which is normal to n, so in general, as we know, it's not a finely parametrized. In general, as we know, it's not a finely parametrized. The surface gravity measures its failure. So instead, let us introduce the finely parametrized normal vector field to n. So which is written by h. So which we can write as follows, where h is some function. So and use a finely parametrized of the horizon. So we can write it as xi equals hu plus some smooth vector field, which vanishes on the null hypersurface. So if you take the killing horizon, given by algebraic equation f equals 0, then this will give us a general form of the vector field normal to the null hypersurface. So okay, so it follows that we write u equals h minus 1 xc plus f v. Good. So then we know that b mu is given by the covariant derivative of the normal vector, and we then calculate Okay, let us evaluate it on the null hypersurface and find its symmetric part. So, yes, because its antisymmetric part, of course, vanishes, because the antisymmetric part is the rotation, which is 0 on null hypersurface. So B mu nu on n. So which terms do we have here? So this term vanishes because the killing horizon is f equals 0. F equals 0, and psi is and since psi is the killing vector field, then it is also 0 there. So therefore we have that this thing equals to psi mu g nu h minus 1 plus v mu g nu f n. However, notice that on n, these three vector fields are in fact parallel on the null hypersurface. So psi mu is proportional to g mu f because again f is 0 everywhere on the null hypersurface, and the only direction it can change is the normal. So gf is proportional to the normal, which is psi, and it's again proportional to u. It's proportional to u. So in other words, if you project B on the orthogonal path, so if we on So if you recall, we had P mu. So if you recall, we had the orthogonal projector P mu nu given by n and u. We then find that B mu nu vanishes. We then find that the orthogonal projection. So B mu nu equals P B P equals 0. Equals 0 since, for example, if we contract u mu b mu nu, we find that this is the same as g nu of u squared, d nu of u squared, which is then 0 on the null hypersurface, and again, if you project u nu on b mu nu, we find that this is the same as d u, which is again 0. Which is again gets 0. So since we defined the shear and expansion with respect to the orthogonally projected B, they're 0. So okay, now let us state the theorem, the zeroth law of the black hole mechanics. So kappa is constant on the future event horizon of a stationary black hole. obeying the dominant energy condition. Okay, so let's start. We know that, we know by the Hawking rigidity theorem that the event horizon in a stationary spacetime is a Killing horizon with respect to some Killing vector field. So let psi be normal to H plus. Psi is the Killing vector field. So by the previous proposition for the Killing horizon, for Killing horizon, the shear and expansion are 0. So therefore, we have that. So my proposition, we have that theta equals 0. That is theta equals 0, and in particular it is constant on the generators. Now, using Raychaudhuri equation, we have that 0 equals g theta over t lambda equals expansion is 0, rotation is 0, shear is 0, equals r mu, psi mu, psi nu. Again, on the event horizon. And using Einstein equations, this is the same as 8p t mu minus 1/2 t g mu. So the Einstein equations read as r mu equals 8p t mu minus 1/2 t g mu, but the second term vanishes because psi is null. So this is the same as H plus. Good. Now, if we introduce the current G mu equals minus T mu nu psi mu, this reads as J times psi on the event horizon is 0. But note that we take the generator of the Killing horizon to be future directed. So future directed and causal vector field. Therefore, by the dominant energy condition, G mu is also future directed and causal. Also future directed and causal. Okay, we clearly see that we're coming to a contradiction. So therefore, since G mu is future directed and causal, as well as psi mu, it then follows that J mu is parallel to psi. So because in general we can define two directions. We can define two causal directions, and the scalar product between the directions should not be zero. And if it is zero, then, well, either the vector itself is zero, or the vector is proportional to, to psi. Therefore, 0 equals j wedge psi. So in coordinates this means as 0 psi mu g nu on h plus equals to minus psi mu t nu rho psi rho on h plus equals again to minus 8 pi psi mu r nu rho c rho h plus. And now recall the Killing vector field lemma that we have proved in the lecture about charges. So this means that kappa over kappa is the surface gravity. Now it then follows that the gradient of kappa is proportional to psi. So the gradient of kappa is proportional to psi. So but psi is normal. So therefore, for any tangential, it's the tangential projection of the gradient of the surface gravity vanishes. That is, kappa is indeed constant on the null horizon, on the Killing horizon. So for any it follows that good. Okay, now we have definitely established under the assumption of dominant energy condition that every stationary black hole has a constant surface gravity, which we can link to the temperature. So in other words, stationary black holes correspond to thermodynamically stable states that we can study, and kappa is one of the macroscopic parameters, the temperature. Okay, now to the first law of the black hole mechanics, which resembles the first law of the thermodynamics, which, as you recall, is a form of energy conservation and energy transformation law. For the black holes, this provides an interpretation of surface gravity as the temperature, well, up to the scale of 8 pi, and the area of the horizon, A, as the entropy. The mass is associated with the internal energy, and angular velocity is a sort of chemical potential. Good. So there are different ways of proving the first law, and in this lecture we will try the most straightforward and the simplest one. In general, the most up to the point proof of the first law, which is a dynamical proof that under the linear perturbations of the black hole spacetime, the first law still holds, was done by Sudarsky and Wald. So, in 1992, and it was dynamical preservation of the first law, where the charges were defined by the ADM with respect to the asymptotics. We will do a simpler proof here. So, since we know that the Kerr black hole is a unique, stationary black hole under certain assumptions, we then expect that the end state is the Kerr black hole, and we will be doing perturbations within the Kerr family. So, namely, we will check that if we perturb the parameters of the solution, which are to the mass and the angular momentum, then the first law holds. Good. So, first of all, we need to find what the values of the potentials and the entropy and the temperature are. Let's remind ourselves about the Kerr metric. So, So this is the curved black hole in the Boyle-Linkist coordinates. The parameter A is the unit angular momentum, per unit mass, and m is the mass. So therefore, we immediately have that m as the mass is the parameter m of the curved black hole, and the angular momentum is A times m. We now need to compute the left-hand side of the first law, which is the surface gravity and the area. So, remind yourself that the null normal to the event horizon of the curved black hole is given by dV, which is the stationary kilevector field, stationary for the asymptotic observer, plus the rotational part, where omega h is a r squared plus a squared. Okay, so we will start with calculating the surface gravity. So as you recall, the surface gravity is computed from the gradient of the square of the norm of the kilevector field. So but let us start with computing the xi squared. So we find that xi squared equals the VV component plus G plus the Vx component plus omega h squared xi component equals to -1 plus 2 mr 1 minus 2a omega h sine squared theta over sigma plus, well, the last part, omega h squared g xi. To simplify the calculation, because, well, taking the derivative of this thing is in general quite tricky, we should notice that xi squared on the horizon is proportional to the dr. Well, first of all, it can be observed geometrically because the horizon corresponds to the hypersurface of constant radius, or constant radial coordinate r. So the norm on the horizon would be dr, proportional to dr. Secondly, it can actually be checked from here, which is an exercise. So r equals r plus equals 1. Good. So therefore, from the definition of surface gravity, it follows that the theta derivative of xi, as well as other derivatives, will vanish. So it follows that the theta of xi squared at r equals r plus is 0. We need to calculate only the radial derivative, which is a simplification, but we can do even better. So since this doesn't depend on theta acts as a parameter here, and since kappa is a constant, we can do the calculation for any value of theta. We will then recover kappa. So let us put it this way. Kappa is a constant. And of course, we take the simplest one, theta equals 0. Good. So when we take theta equals 0, almost all the terms from the square root of from the square of the norm vanish. So the g psi psi immediately vanishes, as well as there vanishes the second term in the bracket. And what we are left for is psi squared theta equals naught is minus 1 plus 2mr over r squared plus a squared. This is sigma at theta equals naught. Now, we only need to compute it. So what follows is that dr of this thing 2mr r squared plus a squared at r equals r plus equals minus 2 kappa, because the norm of the Killing field at theta equals 0 is just dr. Good. So by taking the derivative, we find that kappa, the surface gravity, is given by r plus squared minus a squared, r plus squared plus a squared squared m. This is, although this is the solution, this is not its final form. We can notice some simplifications coming from the definition of R plus. So notice the two relations, which are very useful, and we will use it on the second screen as well. That r plus squared plus a squared equals 2mr plus, and r plus squared minus m squared minus a squared 2 square root of m squared minus a squared r plus. Using this, the surface gravity is then square root over 2 m r plus. Good. Now, on to surface gravity and the actual substitution. Okay. So, area. So let us find the volume element on the spatial cross-section of the horizon, that is on the two sphere of the horizon. So we find that the area element on the S2R plus equals to sigma d theta squared plus something over sigma sine squared theta d psi squared. There should be r plus, yes, it's r plus squared plus a squared squared. So from this, it follows that the square root of the determinant of the metric is, well, the radius times sine theta times d theta d psi, d chi. So the area, which is the integral over of the square root d theta d chi, is a squared integral over the sphere with the standard volume element. So sine theta d chi equals 4 pi plus a squared. Good. So using the formulas from the previous slide, this is the same as 8 pi m r plus. Excellent. Excellent. So we now want to do the substitution. So let us do the left-hand side of the equation. So let us find what 1/8 pi k delta A equals to. So first of all, let me use different color. First of all, notice that the variation of the r plus is the same as the variation of delta m plus m over square root of m squared minus a squared. So let me write it, m squared minus a squared delta m minus a square root of m squared minus a squared delta a, which is the same as r plus over the square root delta m minus a over the square root delta a. Good. So now the variation of 1/8 pi k delta a is the same as 1/8 pi delta, 1/8 pi over, so kappa delta a. Kappa is square root 2mr plus. Delta a is given by eight pi of plus which is the same as square root of 2mr plus so minus a m over the square root delta a, and this whole thing is then r plus 2m delta m minus a over 2r plus delta a. Now to the right hand side, and we find that delta m minus omega h delta j is the same as 1 minus a squared r plus a squared delta m minus omega h m delta a, which is, expanding the brackets, equals to two r plus delta a, which is the right hand side. So which is the left hand side? Good. So in other words, we have verified that for perturbations within the curve family, the first law holds. So this simple proof can be, well, again interpreted as that we consider the stationary solutions. We assume that the curved black hole is stable, so eventually after the perturbations it settles down to the curved black hole, but with a different mass and different angular momentum. And we then treated that the perturbation was within the curve family, so it did hold. Okay, so the second law of usual thermodynamics states that there is a certain thermodynamical function, the entropy, which increases with the evolution of the system. Similarly, here, the analog of the entropy is the surface area of the black hole, and now we show that it does increase. So we have a theorem by Hawking and... So yeah, we have a theorem by Hawking, which states that in an asymptotically predictable spacetime that obeys Einstein and null energy condition, the area of the horizon does increase with time evolution. So, okay. So let G be a strongly asymptotically predictable spacetime. So remind yourself that it means that the exterior of potential black hole regions is globally hyperbolic. Einstein and null energy conditions are satisfied. So let U be some globally hyperbolic region that in particular includes the exterior. So the time evolution is given by Cauchy surfaces, since it's globally hyperbolic. So we can compare the area of horizons on two different Cauchy surfaces. So and sigma 2 lies to the future of the first one. So let h1, 2 are the intersections of the future event horizon with each of the Cauchy surfaces. So this is the horizon, the spatial cross-section of a horizon. And then the area increases. In other words, we have the following picture. So we have two Cauchy slices. We have a black hole here, we have a black hole here. So this is H2, this is H1, and this is the time evolution given by the flow of the generator of the killing horizon, of the event horizon. Good. Yes, of the event horizon. So, good. So, for simplicity of the proof, we will also assume that horizon is non-singular in the sense that the inextendable null generator of the event horizon is future complete. So in principle, one can prove without this assumption, but it needs some workarounds, and for simplicity, we will let it slip. Good. So the proof goes as follows. First of all, we show that the expansion must be non-negative. So the area of the horizon either increases or remains null. And then, well, from this directly follows that the area behaves as this. So let's do a proof by contradiction. So let theta at some point p be less than 0, and p lies on the event horizon. So let's gamma be the null generator passing through the point p. So gamma is the null geodesic passing through the point p. So since the expansion is negative and we assume everything to be smooth, we can take a point, or at least somewhat regular. We can take a point near p on gamma. So take q on gamma as well, q to the future of p, and q sufficiently close to P such that the expansion at Q is also negative. So since we're taking the functions to be at least continuously differentiable, we can always have such point Q. Now, if you recall from the theorems about the causal structure, if you have a point with negative expansion, and since we assume that the generators of the horizon are non-singular, that is, they are future complete, then we immediately have a conjugate point to P on gamma. There exists a conjugate point R. So, in other words, what we have is that if this is a larger horizon and we have the negative expansion, then, so if this was point P, if this was point Q, then at some point in the future, we will have a conjugate point R such that we had another null geodesic going through P and then goes through R again. So this is of course a terrible problem. So this is of course a critical violation of all geometric structure of the event horizon that we can imagine, and in particular, since there exists a conjugate point, it means that the null generator gamma, which is a causal, so a null curve, can in fact be deformed into a time-like curve connecting P and R, which means that the event horizon is chronal manifold, which is in contradiction with the causal structure. It's of course as the boundary of the region accessible to infinity, it's of course achronal, as we have proven in a corresponding theorem. So exists there exists a deformation of gamma time-like curve connecting Good. So now we have then that the expansion is non-negative. So good. So now recall that the null generators define a time flow of the spatial cross sections of the event horizon. So here the time evolution, because, well, this can be seen from this picture. So if H1 is the spatial cross-section at the time T1 of the Cauchy surface 1, and H2 is similarly for sigma 2 at the time T2, then, well, the evolution is given by the null generator of the horizon. So, in other words, the null generators define a map from H1 to H2. So, define a continuous map from H1 to H2, and from this we have that area of H2 is definitely greater or equal than the image of this map, which is greater or equal than the area of H1, because H1 because of the non-negative expansion. Good. So we have just shown that the area indeed does not decrease with time evolution. So besides the two laws of the black hole mechanics, there is of course the question about where there is an analog of the third law of the thermodynamics. There is, to some extent. So as you recall, there are different formulations of the third law in thermodynamics. One is that any isothermal process at temperature equals 0 is also isoentropic. So in other words, the processes that preserve 0 temperature also preserve the entropy. There is a stronger formulation of this thermodynamic law, which says that the sort of the vacuum, the minimal energy state corresponding to temperature equals 0 is unique. And therefore, we can set the entropy equals to 0. So, of course, this is not paralleled by the black holes, because if we set temperature equals to 0, we'll get extremal black holes. But extremal black holes they're still black holes. They have non-zero horizon areas. So, in other words, at temperature equals 0, the black holes have non-zero entropy. So there is a formulation of the third law, which holds for space-time satisfying dominant energy condition. It says that the extremal black holes, that is black holes with 0 surface gravity, cannot be obtained from regular black holes with non-zero surface gravity by any finite number of physical processes that such as addition of certain matter, etc., as long as this matter satisfies the dominant energy condition. As a conclusion, so since this is the last lecture, I would like to give a conclusion to this course. So in this course, we have covered the basics of the black hole theory and we try to cover the state of art of the problems in mathematical physics, in mathematical general relativity, related to the black holes. Some topics, unfortunately, didn't make it into this course, such as, for example, the perturbations of black holes and the quasi-normal modes. We could, of course, talk more about the black hole thermodynamics, providing more examples. And we spoke pretty much nothing about the numerical problems. That is about the parent horizons, and we covered the bare minimum of the trapped surfaces. Also, we didn't speak much about another aspect of the black hole uniqueness theorems, that is the solution generating techniques. So, in 4 dimensions, the particular structure of general relativity allowed for certain simplifications of the Einstein equations as partial differential equations that allowed to prove the uniqueness of the solution. In higher dimensions, this is not the case, and instead one has a more complicated structure where the black holes are not unique, but instead are encoded by a certain topological structure called rod structure. These are, of course, ongoing topics, ongoing research topics, and it's in an active field of obtaining and classifying solutions in higher dimensional theories, in particular in theories with supersymmetry, which brings direct relevance to the string theory. So another topic not covered in this course were the asymptotic symmetries of the spacetimes. This, of course, is a very large topic, and it would require at least a couple of lectures on its own to cover the basics. But we have slightly touched the subject. We have slightly touched the subject when we were defining the asymptotic conserved charges, the asymptotic mass and angular momentum by the ADM definition. So I'm trying to keep this course up to date, and so hopefully in the next version of this course I would cite more new fundamental papers that would appear. Thank you for your attention.